Okay guys, in this video we're going to be looking at how to solve a 3 by 3 system of equations. That is a system that has 3 equations and 3 variables here. And what we're going to be focusing on is the nature of our solutions as well as the row operations that we take in order to rewrite this system into a more convenient form that we refer to as row echelon form. Okay? And so let's go ahead and start by looking at the system that we're given here. You're going to notice that I've chosen to look at a system that is missing several of our variable values here, or we could call this maybe like a sparse system. But what we're essentially trying to do is find an ordered triple, we would say some x comma y comma z, that all 3 of these graphs have in common, or at least that if I substitute back into each of these 3 equations should make them true. So graphically speaking, what I want you to understand is that each of these equations actually graphs what we call a linear plane. And so you're going to see over here on the right here I have diagrams of several different types of linear plane situations, but in this case I'm going to tell you that I chose a system that is going to have one and only one solution. So that is to say that if I had 3 linear planes that all intersected in 3 space at this point right here, then this would be the common solution for each one, graphically speaking. Looking at systems to come, we'll look at some systems that perhaps have more than one solution. That would be something like you see here. All 3 planes intersect along this line that kind of extends forever and ever in this direction, but we would say there are infinitely many ordered triples that lie along this, and so infinitely many solutions. Or it could be that all 3 of our equations are actually the same equation and they graph the same graph, meaning that all 3 of these planes would intersect at every single ordered triple on these planes. And then for our no solution cases, we would just be looking at a situation where all 3 of these planes may do what they need to do, but they never ever intersect all 3 of them at one point or one common set of points. And so we're going to search for our solution to this system by rewriting into what we call row echelon form. And row echelon form, you're going to notice a lot of time, tends to look like this when it comes to a system. But we're going to rewrite all 3 rows so that what we see in each row is just this stair-step pattern where you kind of get your terms to come in like this, and that each row starts with a leading 1. And the benefit of doing something like that, or rewriting a system like this, would be that we would already know what z is equal to. And let's say I had, so many z's here. I don't know how many, but I would have, plus maybe so many y's here plus so many z's. But if I knew z, I could back solve by plugging that back into this equation and going and solving for y. And once I know y and z, then I could plug those back in for y and z in this first equation and go solve for x. So the advantage to having something in what we call row echelon form is that each row does have a leading 1 and we'll already know the value of our final variable here, z. So in order to rewrite this into a row equivalent system, or an equivalent system that has the same solution as what I started with even though it looks different, we can use these 3 operations. So let's recall that we are allowed to do these 3 things when it comes to solving or rewriting our systems into a row equivalent system. We can change 2 rows around. We can multiply a row by a non-zero constant. We give this a name. We call it a scalar. It scales our equation up or down. Or we can add a scalar multiple of one of these equations to another equation, and this is the important part, to replace the equation that we added it onto, but not the one that we scaled. So if what we want to do here, let's go ahead and get started. If what we want to do is write this into row echelon form, our goal is always going to be starting by getting a 1 in the top left corner. And so if I want to get a 1 in my top left corner here are my choices. I can rearrange my rows, swap rows, or what I could do is I could scale this top row down by a scalar. Now what I know is that anything times its reciprocal gives me 1. So what my goal is going to be here to do, and I'm going to write my step over here on the right, but we always write our work here. I'm going to say I'm going to take 1/2 and I'm going to multiply row 1 by a half, where this is our first row. So what this does is it produces a new system that is row equivalent to the original, but we would have, instead of 2x, we would have 1x. If I took 2z times a half, I would have a 1z, and if I took 2 times a half, I would have 1. So our new first equation is going to be that there. We're going to rewrite our second and third equations here just to kind of rewrite our system. So let's get that out of the way. 4. And then we'd have 3y minus 4z's equal to 4. Now the idea is once we get a 1 in the top left corner, we're going to use that 1 to add scalar multiples of row 1 onto any row below it so that we can get everything underneath this x to become a 0. That is, when you look at this row echelon form, once we had a leading 1 here, there was nothing left underneath it. So our goal is to target this 5x here. And the real question is, what could I add to 5x to get it to become 0? Well, naturally it would be negative 5x. So the idea is going to be that once we get a 1 here, we're always going to use this leading 1 here to multiply it by the opposite of the thing we're trying to cancel out. That is to say that what I'm going to do is I'm going to take row 1 times negative 5. So negative 5 times row 1, and I'm going to add that on to row 2, thus only affecting the latter equation, which will be only affecting row 2. So if I do this here, neat thing is, my first row, even though I said take it times negative 5 and add it to row 2, it only affects the equation that I'm adding it onto. It doesn't affect the fact that this is x plus z equals 1. As a matter of fact, what I'm going to say is once you get this leading 1 here, then the first row should never change throughout the rest of this process ever again. Now let's say that I do add negative 5 times this 1 here plus this 5 here. Well, negative 5 times 1 is negative 5, and negative 5 plus positive 5 is 0. So effectively, we've canceled out the x underneath it, but we have to go ahead and do this for every entry in row 1 and add it to row 2. So we would say now next, negative 5 times this 0 here, which would be 0, add that to this 3 here, what I would get is still 3y. If we take negative 5 times this positive 1z, we get negative 5z, and negative 5z plus this 0 here would be negative 5z. And then if we did negative 5 times this 1, which is negative 5, and add it to this 4 here in row 2, negative 5 plus a positive 4 is a negative 1. In our third row, as a matter of fact, we didn't do anything with it. And so what we end up with is this new row equivalent system, but the neat thing about this is we have our leading 1 here and nothing underneath. Once we have gotten our leading 1 and eliminated everything underneath it, our goal next is going to be get a leading 1 in the second row. So I notice in my second row it begins with a 3 here. One way to get a leading 1 is to multiply the whole second row by a third, which I can see already is going to produce fractions. But my only other alternative is to switch rows 2 and 3 around, and then I'd still have to multiply this one by a third to get it to become a 1, which also produces fractions. So I'm kind of keen on just doing this. Let's just say we're going to take row 2 times a third. So what this is going to do is it's going to produce a new row equivalent system. Our first equation, remember what I said, is now kind of the same. We are going to get our leading 1 now on our second equation, taking 3y times a third, which gives us just 1y. Now I have to take a third times my negative 5z, which is going to give me negative 5 over 3z, and I also have to take my third times negative 1 over here, which gives me a negative 1 over 3. And then our third equation would still stay the same. We didn't do anything to it. So the whole point of getting a leading 1 here, of course, is to use that leading 1 to cancel out everything underneath it, which I see a 3 underneath this. So the reason why we get a 1 is because it makes it real easy to determine what could I take times this 1y to get to add up with my positive 3y to get it to cancel out. And of course the answer is always going to be take this 1 times the opposite of this thing underneath that you're trying to cancel out. So what my goal is going to be here, or is going to be here, is we're going to take a negative 3, which is the opposite of this positive 3. We're going to multiply that by row 2, and we're going to add that on to row 3. So, rewriting my system, row 1 doesn't change. As a matter of fact, now row 2 has a leading 1, so it's always going to be the same from now on out. Y minus 5/3 z is equal to negative a third. And then if we were to add now negative 3 times row 2 plus row 3, well, I know that negative 3 times 1y is negative 3y, and negative 3y plus this y here is 0. So we've effectively canceled out the y underneath this. Here's where we're going to have to do some fraction math. Now I have to take negative 3, try to show you my work here, negative 3 times this negative 5/3 you see right here, and we're going to add that onto this negative 4. So negative 3 times negative 5/3, and we're going to say plus a negative 4. So looking at this, we know we multiply fractions straight across here, but I notice that these two cross cancel and I get a negative 1 here. So negative 1 times a negative 5 is really just a 5, and 5 minus 4 gives me a 1. So what that means is if I do negative 3 times a negative 5/3 z and add that to 4z, I'm going to get left with just a 1z. We have to do the same thing here with our constants next. We're going to take negative 3 times this 1/3 negative in the second row, and we're going to add that on to the constant in the third row here, which is 4. But again, what I see is I get these to cross cancel, which doesn't always happen, but is nice when it does. I get negative 1 times negative 1, which is 1, and 1 plus 4, which is 5. So this means something. It means that, first of all, before I get too excited about that, it means that now, looking at our system, we are in row echelon form. That is to say, we have this stair-step pattern, and each row has a leading coefficient of 1. But the next thing I can say about that is that's beneficial because now we know exactly what the value of z is. So I'm already going to get a little spot working over here that we're going to say is solution. And what I'm going to put is some ordered triple here where our z value must be 5. So now the idea of having this in row echelon form is now that I can take this 5, I know that z is 5, I can put it back in my second equation here. So I'm going to go ahead and do that. Y minus 5/3 times z is equal to negative 1/3. And what we're going to do is we're just going to simplify this and solve for y. So what I get here, multiplying my fractions straight across, is y minus 25 over 3 equals negative 1 over 3. And by adding 25/3 to the right side, we get y by itself. So this means that I have a total of 24/3, which in this case is pretty awesome because it means that it comes out to be a nice integer value, which is not always guaranteed. But now the beautiful thing is I know y and z. So to find x, what we're going to do is we're going to go now substitute these back into our first equation, which is kind of neat because you'll notice that we're actually missing a y value. So when we rewrite this x plus z equals 1, I really only need to substitute in for z here, but I get x plus 5 equals 1. And subtracting the 5 to the other side, we basically determine that x is negative 4. So this ordered triple here, what we want to acknowledge is that really if I were to go back and graph all three of these linear planes, say that's something I could do, then the point at which all three of these are colliding is at negative 4 on the x, positive 8 on the y, and positive 5 on the z, that point in space. Okay. So recapping, we want to start by getting a leading 1 in the top left and use it to eliminate things underneath it, followed up by getting a leading 1 in the second row and using it to eliminate things underneath it, and then getting a leading 1 in the third row if necessary. But once you do that, we're just going to back solve into each equation to find out what our solution is. Cheers.